So on Wednesday and Friday of last week, we effectively established the ground rules for performing circuit analysis in the frequency domain. So today I'm going to work a couple of examples, literally 2 to 3 tops that I'm going to ask you guys what you feel like you need the most review on. We're going to do that on Wednesday, and then we're going to move along to bigger and better things. Sound like a plan? All right, so the first circuit that we are going to look at is this guy here, where we have some voltage source Vs of t connected to a 200 microfarad capacitor, in turn connected to a 30 ohm resistor. Here we have a 10 ohm resistor. Here we have a 50 millihenry inductor. And our goal is going to be to solve for this current Ix of t when our source voltage Vs of t is supplying 40 sine 200t minus 20 degrees volts. So I sincerely hope that I have convinced you all, with the terrible amount of trig identities and stuff that we had to deal with on Friday, that you would never actually try to work this problem in the time domain. Instead, we will convert it into the frequency domain and then use our regular DC circuit analysis techniques in order to do the math. All right. So I am going to convert this into the frequency domain first by replacing all of my voltages and currents with phasors. And then I'm going to replace all of my resistors, capacitors, and inductors with their impedance at our frequency of interest. And then we can do our analysis. So let's start with our source voltage, Vs. What is the phasor equivalent voltage here? So 40 in magnitude, I agree with that. What about the phase angle? Negative 110 degrees, because we need to convert it from sine to cosine first, which involves subtracting 90 degrees from the phase angle. Negative 20 minus 90 is negative 110 degrees volts. All right. Now I'm going to convert my unknown quantity Ix of t into its phasor equivalent. So I literally just write it as Ix with a bar over it. My voltages and currents have been converted. Now I will convert all of my passive components into impedances. So as we know, the impedance of a resistor is just the resistor value itself. So the 10 ohm resistor is going to continue being a 10 ohm resistor. The 30 ohm resistor is going to continue being a 30 ohm resistor. The impedance of an inductor, ZL, is given by J omega L, which is going to be J. So what's omega in this case? 200 radians per second. L is 50 millihenry. And just so I don't screw this up, I will use my calculator. So 200 times 50 times 10 to the minus 3. So positive J 10 ohms. For my capacitor, this is going to be 1 over J omega C. That's going to be 1 over J times 200 radians per second times C was 200 microfarads. Looks like negative J 25 ohms. And now we have converted our circuit from the time domain into the frequency domain. Because 1 over J is the same as negative J, which I showed you guys last time, the impedance of a capacitor will always be negative. The impedance of an inductor will always be positive. All right, so now we need to choose how we're going to analyze this thing. And the short answer is we can analyze it however we choose, okay? So I would like to take suggestions from you guys. I have an idea of how we might do it fairly easily, but I want to see what you're thinking about. Andrew, you're looking very contemplative. Tell me what you're thinking. You weren't thinking. Okay, Jake, how about you? So Jake has suggested mesh analysis. So I'd like to talk about that briefly here. Mesh analysis is absolutely fair game. However, in order to solve the system, we would need to use a computer algebra tool because the calculators that we have on hand literally cannot solve systems of equations with complex numbers. So we could do this with mesh analysis, whip out MathCAD and all that kind of good stuff, but let's think of creative ways to do this that will allow us to solve it just using our calculator, since I'm going to expect you to be able to do this kind of work on your next exam. Brody. We could do that. So the suggestion would be to find the voltage drop across the 30 ohm resistor, and then from there we could do what? The two impedances on the right. Okay, so if we found the voltage drop across the 30 ohm resistor, then we could indeed just use Ohm's law to find the current Ix. Absolutely, that's one way that we could do it. Anybody else have a suggestion? Yes. So current division requires us to have a current source. Okay, so the suggestion from Mr. Parker is to find the equivalent impedance of the entire network, to find the current that flows through the minus J25 ohm capacitor. And then from there, we could do current division. That's also one way that we could do it. Cade. Source transformation would actually work here as well. And then once you do a source transformation, you could do current division. That's what I see when I look at it. I actually see this is a great opportunity for us to do source transformation. It's also a pretty good opportunity for us to do, I'm going to call it nodal analysis, but really it's just an application of Kirchhoff's current law. So let's do both of those things to show you what's up. So method number one here is going to be source transformation. And current division. I'm running out of space. So we're going to start by doing a source transformation. So this is going to follow the same rules as source transformation for DC circuits did. So since the positive polarity terminal of the voltage source is on top, the current is going to be flowing up. The amount of current that is being provided is simply going to be our voltage, 40 angle negative 110 degrees volts, divided by the impedance that is connected in series, which was minus J25 ohms. And I'm just going to leave it like this for now. If we have calculators, we could figure it out, but it's not adding any particular value to our analysis. Now we put our negative J25 ohm capacitor in parallel. This will be in parallel with our 30 ohm resistor. And then this box over here on the right is representative of a generic circuit element. And we know that the impedance of this generic element is going to be 10 plus J10 ohms. So we're effectively just lumping those two impedances in series into a single equivalent impedance. And our current IX is the current that's flowing through that 10 plus J10 ohm equivalent impedance. So from here, current division is going to be pretty straightforward. We could say that IX is going to be 40 angle negative 110 degrees volts divided by minus J25 ohms. We're going to have 1 over 10 plus J10 divided by 1 over negative J25 plus 1 over 30 plus 1 over 10 plus J10 ohms. And now we just need to throw this into our calculator. I'll give you a fair warning. The TIs should be able to do this all in one go. Sometimes the Casios can be a little bit finicky, and it might be of better use to you to break it into two parts. One for the current on the left, another, store that as a particular variable, then do the ratio, store that as a particular variable, and then just multiply those two variables together. These are the results that I got in both polar and rectangular forms so that you can see whether you got it correct. This is making the potentially large assumption that I typed everything into my calculator correctly, but I see at least one thumbs up. So unless Travis and I made the same fat finger mistake on our calculators, it's likely the correct answer. Anybody else get this? Okay, good deal. All right, so multiple people have gotten this answer, so let's go out on a limb here and assume that this is correct. Is this level of analysis difficult? I would argue no. We haven't done anything remotely new here. We are just using complex numbers to use the DC circuit analysis techniques that we outlined previously. All right, so let's look at method number 2, which is one that I like to do a lot, and this is effectively what Brody had suggested. Actually, this would be nodal analysis and Ohm's law, not voltage division, because we're not trying to find a voltage. So I'm just going to redraw my frequency domain circuit here. And what I'm going to do is at the negative polarity terminal of my voltage source, which is down here, I'm going to choose this to be my ground. And I'm going to call this node X with a voltage, nodal voltage Vx, which happens to be the voltage drop over the 30 ohm resistor, which is what Brody had indicated. So if I apply Kirchhoff's current law at node X, let's start over here. I'm going to have Vx minus 40 angle negative 110 degrees volts over minus J 25 ohms plus Vx over 30 ohms plus Vx over 10 plus J 10 ohms is equal to 0, where once again, I'm treating those two impedances in series as just a single equivalent impedance, thereby eliminating that node from my equation that would occur in the top right-hand corner, so that I have a one equation, one unknown system. Now, our calculators, if you use the numerical solve tool on your TIs, or if you use the solve function on your Casios, still can't solve this, even though it's a one equation, one unknown system. That being said, we're like 2 algebraic steps away from solving it our own damn selves. So that's exactly what we are going to do, okay? So let me scroll to the next page here. So I'm going to have Vx multiplied by, and I'm going to have to go back and forth here because I can't remember everything. So I'm going to have a factor of negative 1 over negative 25 ohms. So 1 over negative J 25 ohms plus 1 over 30 ohms plus 1 over 10 plus J 10 ohms is equal to 40 angle negative 110 degrees volts over minus J 25 ohms. And what's interesting is effectively when we divide the right-hand side by this 1 over J25, all this kind of stuff, it actually winds up being effectively the exact same thing as the current division that we had just done, or pretty darn close to it. Anyway, so what I would do here is I would do all this math to give me a number that I'm going to store in my calculator as variable A. That's 1 over negative 1 over 25I plus 1 over 30. Actually, hold on, I don't need this 1 over at the top. Getting ahead of myself. If I made an algebraic mistake, I hear a lot of whispering. If I have, please let me know. Let's see, this would be ohm. Storing this as A. Over here on the right-hand side, this is going to be B. And from this, we could see very easily that Vx is simply going to be B over A. Our calculators can easily give us. And so I get 18.563 minus J 4.339 volts. And from here, our current Ix is simply Vx over 10 plus J10. Or 0.711 minus J 1.145 amps. Or in polar form, 1.348, angle negative 58.157. The exact same results we got earlier, right? Two entirely different methods, both roughly the same level of difficulty, giving us the exact same answer as would be expected, okay? So I am effectively trying to forewarn you that for this section of the class, at least for the material on your exam, you are not going to be able to rely on mesh analysis as the crutch that many of you have relied on to carry you through to this point. Unless, of course, you are willing and or able to learn how to use Cramer's rule to solve that systems of equations by hand, which you're more than welcome to do. But I would argue that it'll take you much longer to get the result that way than it would be just learning how to do it a different way. So, anywho, so you're going to have to start thinking a little bit more creatively about how to get these problems to work based on the constraints of what our calculators can actually do. So KCL, KVL, source transformations, superposition, things like that are going to come back in a big way here in order to avoid us having to use a computer to solve these things. For your homeworks, you can use the computer, anytime that you feel it is appropriate, but on your exams, that's flat out. So you at least you need to have some practice of figuring out how to do these by hand. All right, so let's work one more problem and we find something. All right, so let's say that VS1 of t is 21 cosine of 10 to the 5t volts, and VS2t is 10 sine 10 to the 5, and I need the t to be down here, volts. And our goal is to determine current flowing through our 1 microfarad capacitor on the right. So what's the first thing we need to do? Convert this thing from the time domain into the frequency domain. Absolutely correct. So what is VS1 going to look like in the frequency domain? What is its phasor equivalent? 20 angle 0 degrees volts. 21, thank you. What about our voltage source VS2? What's it going to look like in the frequency domain? All right. Now I'm going to convert our, sorry, this should have been ahead of myself, Ix of t. Converting this current into the frequency domain, we just replace it with a phasor current. Our 5 ohm resistors will remain 5 ohm resistors. What is the impedance of our capacitor going to be? Use the equation like 7 minutes ago or something. 1 over j omega c. All right, so plug the numbers in. What do you get? Exactly right. So how do you think we should solve this? So I'm going to suggest something here that we haven't actually used a lot as a circuit analysis tool, but that we do know how to do. I am going to suggest that we use a Thevenin equivalent circuit here to aid in our circuit analysis. And so what I mean is I'm going to draw a dashed line here. We're going to disconnect everything to the left of that dashed line, find the Thevenin equivalent, and then replace it. And that would vastly simplify the network that we're looking at. Okay. So our left-hand network looks something like this, where this is our Thevenin equivalent voltage. So what should VTH be? Anybody have any thoughts? I'm not looking for a numerical answer just yet. It's not that obvious to be able to do that. The voltage drop across the negative J10 ohm resistor, absolutely correct. Since there's not going to be, sorry, that looks like a 50 much more so than a 5 ohm. My apologies there. We could do KVL, but I'm going to do voltage division because I'm lazy. I want a voltage and I know a voltage. So let's do voltage division. So understanding that there's no voltage drop across the 5 ohm resistor on the right, we can say that this is going to be 21 angle 0 degrees volts times negative J10 ohms over 5 minus J10 ohms. And I'm going to throw that in my calculator. So I get 18.783 angle negative 26.565. Anybody have any problem with that level of analysis? Fairly straightforward, right? What is our Thevenin equivalent resistance going to be, or impedance in this case? Well, we need to be looking at a dead network, so we turn off our voltage source. We have a 5 ohm resistor here, a negative J10 ohm impedance here, a 5 ohm impedance here. We're looking in. So to me, this looks like 5 ohms plus 5 ohms in parallel with negative J10 ohms. I'm going to throw this in my calculator. So that's 5 plus 5 times negative 10I over 5 minus 10I. Looks like 9 minus J2 ohms. Anybody else get something? So assuming I'm correct here, now what we would do is simply replace everything to the left of the dashed red line with its Thevenin equivalent. So we would have, give myself enough room, and 18.783 angle negative 26.565 degrees volts in series with 9 minus J2 ohms. And now we connect this to everything to the right of the red line. So we have our capacitor that was minus J10, I think, through which our current IX is flowing. Here we have our 5 ohm resistor. Here we have our 10 angle negative 90 degrees volts source. And I would argue this just got much easier to analyze, right? So we could do something like we did a moment ago, where we effectively do Kirchhoff's current law at that topmost node, solve for that voltage, and then that voltage divided by minus J10 ohms gives us the current that we're looking for. We could also easily do superposition now if we wanted to. We are 1 to 2 steps away from getting the result that we want using a multitude of different circuit analysis techniques by breaking this thing down into smaller pieces and using the Thevenin equivalents to aid us in our circuit analysis. Okay. So using that modified nodal analysis technique, because to me it's pretty straightforward and gets us the answer that we're looking for pretty quickly, we would have Vx minus 18.783 angle negative 26.565 degrees volts, all over 9 minus J2 ohms, plus Vx over negative J10, plus Vx minus 10 angle negative 90 degrees volts, all over 5 ohms, is equal to 0. That looks too much like a 6 for my comfort. And because I didn't give myself enough space, we'll go to the next page here. So this is going to look like Vx times 1 over 9 minus J2 plus 1 over minus J10 plus 1 over 5 ohms will be equal to whatever VTH was, I can't remember, over 9 minus J2. And then I want to say it's going to be plus 10 angle negative 90 degrees volts over 5 ohms. Let me just double check that. So the minus sign, yep, all that seems legit. So now I'm throwing things into my calculator. So over here, this thing looks like 0.330, angle 21.991 degrees per ohm. Storing that as A. On the right-hand side, I have VTH, which I have stored in my calculator over 9 minus 2i plus 10 angle negative 90 over 5. Storing this as B. .182 angle negative 51.605 degrees amps. Vx is B over A. Comes out to be 9.647, angle negative 73.596. And the current Ix that we're looking for is Vx over negative J10. Comes out to be 0.965, angle positive 16.404. Degrees. All right, so I have ranted enough for today, in my opinion. Actually, let me do one thing here that I forgot to do on the last problem, okay? And then I will stop ranting at you for the day. So what I forgot to do on the last problem and what I'm about to do here, we were looking for this as a function of time and we solve for it in the frequency domain. So one thing that we do need to remember to do is to convert back. Well, that conversion back is trivial. We know the magnitude, we know the phase angle, we know our angular frequency. So it's literally just plugging those things into our expression. So Ix of t is going to be 0.965 cosine 10 to the 5 t plus 16.404 degrees, which I should have done that on the last problem as well, because we started in the time domain, so we should end in the time domain. But that's a fairly trivial thing to do. I just wanted to remind you of it, because you're going to be expected to, you will be expected to do that on your homeworks and possibly your exams and stuff like that as well. Other times you might be just given the circuit in the frequency domain to start with, which means you don't have to do all of the steps that were involved converting to the frequency domain, and then just do the math. But anyway, so I'm done talking for the day. There is an in-class assignment that you guys can work. How many problems is it? Two problems. You're really free to do it however you want. Before you get cracking on that though, what do you want me to talk about on Wednesday? We do have a lab, but I have roughly an hour worth of time to review things. Tell me what you feel our time, excuse me, would be best spent on.
So that this can be done with
Steady state sinusoidal analysis, the name implies that transient analysis has died out because we are at steady state. So these are two kind of separate things. Transient analysis on these types of circuits can be done. So for instance, right now we are effectively assuming that our circuit has been sinusoidally oscillating since the beginning of time, which likely isn't true. We have to turn on our sinusoidal sources at some point. That being said, the way to do that isn't a huge time sink is to use circuit analysis in the Laplace domain, which not all of you guys know how to do. So we are not going to do it. That is beyond the scope of this class. If and when you go further into your electrical engineering classes, then we'll get into that. So for us, steady state sinusoidal is as quote unquote difficult as it is going to get. We're not going to put transients on top of this analysis. And I don't want to remember how to do convolution integrals in the time domain because they're just annoying. So to this point, no one has suggested anything for the review-ish type thing on Wednesday. If you guys feel comfortable, we can just do the lab on Wednesday. I don't have a problem with that. But somebody has to have something that we did 3 months ago or 2 months ago that they're not super familiar with. Lucas. Sure, absolutely. So Thevenin and Norton with dependent sources, I can do that. Anything else?
I have a question about like op amps on the test. Is it just going to be like what we did in class, with just analyzing them, finding V out?
For the most part, yes, but I could throw you guys a curve and make you analyze a circuit, an op amp circuit in the frequency domain. So we could do an op amp circuit using this stuff as well.
If you don't mind doing
Yeah,
that.
not at all. So Thevenin and Norton with dependent sources, op amps, anything else? I need to talk to Dr. Swanbaum and Dr. Kronk about that because I suggested that exam 3 not be cumulative at the beginning of the quarter. They agreed to it then. I want to see if they still agree to it now. The reason that I want the exam to be non-cumulative, covering only op amps and then the steady state sinusoidal material, is that I tend to see electrical engineering students completely check out for this section of the class because they usually have a good grade in place. And then if the exam is, the final is cumulative, they know that they have roughly 60% of the material already mastered. And so they tend to stop giving a crap about learning anything new. That is problematic in their later classes. So I am trying to avoid that by making this count as a real test, all on this new material, so that my EE students don't totally slack off here because I'm a jerk. So I will go with the majority rule. If Dr. Swanbaum and Dr. Kronk feel that a cumulative exam is more appropriate, I will not fight them on it, but I am pushing for the other route. Daniel. Superposition, sure. So superposition, Thevenin and Norton equivalent circuits with dependent sources and op amps. All right, so that's 3 things. So we'll work 3-ish circuits and call it a day.